So this again is chapter 10, and we're talking about properties of solutions. We finished up a second ago talking about, again, those colligative properties, which are all based upon how much particles are dissolved in those solutions. And as we saw here towards the end, it does make a difference the type of solute particle that's dissolved. If it's a non-electrolyte, again, you get kind of a one-to-one sort of relationship in terms of the particles that end up in the solution. But if it is ionic, as we saw in the last few examples, you do need to take into account how many particles are going to go into that solution. And again, that's the von Hoff factor, which is abbreviated with the I. And as we saw in that sort of second to last calculation, sort of the measured value and the one that you would predict based off the formula, they will be slightly different, but they're very close to one another. So in pretty much all problems that involve sort of an ionic sort of situation, if you need to use the von Hoff factor, you can just use really the equation and how many ions it breaks apart into to figure out what the value of I is, and you'll be okay. So to finish up this chapter here, a few more sort of properties of solutions. We talked a little bit earlier there when we were talking about osmosis, and we'll talk about that and again here in a second. A semipermeable membrane is a membrane that, again, allows certain size sort of particles to really pass through. Oftentimes you can't see it even if you look at a membrane, but there are kind of like holes in it. And again, that allows those certain size guys to have no problem to really sort of pass back and forth pretty freely. But if you did have sort of a larger sort of molecule, it's obviously going to have a pretty hard time to try to get through those little holes, and it'll be really excluded. There's different types of solutions sometimes we refer to. There's ones known as colloids, and these are really larger sort of solute particles. They are proteins or groups of molecules that are together. They are homogeneous mixture. So colloids are homogeneous, which, as we've talked about, means that it looks the same throughout. It's just like a homogeneous, obviously, mixture in that sense. They are small enough to pass through filters, but they do get a little hung up trying to get through the membranes. So if you use something like a filter paper, you'll be able to sort of pass that through a filter paper. But if you try to use a membrane, it will get really caught up. Suspensions, on the other hand, are heterogeneous type of mixtures. And heterogeneous means that you do see different phases and stuff like that. So a heterogeneous, or really a suspension, is something that you can really see with the naked eye. You can see something floating around in it. So for example, obviously, if you had, say, sand and water, that's a suspension of sand in water, and you could clearly see the sand in the water if you looked at it. They are too large. They get trapped both by filters and also membranes. And here's sort of a zoomed in of a membrane. And again, you can see here, there's really sort of channels. And again, sometimes cells and membranes and stuff work like this. But again, it allows certain size guys to be able to pass through. So these smaller guys and solvent molecules like water are going to have no problem. But again, these larger guys, they are going to get sort of hung up there as they try to go through it. And here's what we talked about: a solution, which is a homogeneous mixture along with a colloid. If you put it through a filter paper and sort of filter it, they will definitely pass through with no problem. But here are suspensions, which again are those heterogeneous sort of mixtures, would get caught up there. So again, a simple example, that's what I was just mentioning. If you took your sand and water, you would pass the water through no problem. But the sand obviously would get caught up on the filter paper, right, and wouldn't pass through when you did that. This is a membrane, kind of like a dialysis bag here. And again, same idea. There's little holes on this bag, and it's going to allow certain size molecules to transfer through. So solution sort of guys will be able to kind of pass through with no problem, but it will sort of catch up those colloids and suspensions, which are a little bit larger and sort of get trapped in there. That's sometimes in labs, how people will sort of prep proteins. If you want it in a particular sort of environment, like a pH environment or something like that, you could drop your protein in a bag basically like that in a buffered solution at a specific pH and leave it in there. And basically the protein will be stuck in the bag, but it will now allow right, the environment or that pH sort of to go into the bag. And now you got your protein in sort of the same sort of pH as maybe you might want it in the body or something like that. And you can go do your experiments sort of in the same sort of situation. All right. So we talked a little bit earlier about osmosis. And again, that is the flow of really solvent molecules from that lower concentration to the higher concentration. Again, really in an effort to sort of dilute it out, the higher concentration. And as we talked about, it will continue to flow across that membrane until it hits that osmotic pressure, which again, in that little tube sort of drawing that I did, it will flow, say, from the water side to the other side until it basically hits that osmotic pressure, and then it will stop. The osmotic pressure of a solution is dependent on the more particles that you have in that solution. So the greater the amount of particles, the greater the osmotic pressure that we would see. Water has no osmotic pressure, pure water, again, because it has nothing dissolved in it. Another sort of quick way that sometimes people will calculate or think about osmotic pressure as another sort of unit of sort of pressure, and that's sometimes referred to as osmolarity. And osmolarity, sometimes referred to as just osmol, is basically the I, which is the von Hoff factor, times the molarity of a solution. So for example, if we had 3 solutions, we had our sodium chloride solution where I was 2. We had our calcium chloride solution where I is 3. And if we had the same molarity of each of these guys, as say 2.5 molar of each of these guys, again, we would calculate the osmolarity of it by taking, for example, the sodium chloride. We would take 2 times the 2.5, going to give us 5 osmolarity. And then obviously here we would take our 2.5 times our 3 for our other guy, our calcium chloride. Going to give us 7.5 osmolarity. So our calcium chloride, as we would expect, would have a sort of higher osmotic pressure and so that osmolarity sort of calculation versus our sodium chloride here that has less particles basically floating around in that solution. So sometimes osmolarity is used with osmotic pressure as a way of figuring out, sort of concentration wise, if you have just the concentration of a solution, you could kind of quickly figure out, kind of which one would have a greater sort of osmotic pressure. Any questions on that there? And there is sort of our prettier picture of what we got going on there. Obviously, a brine is more of a salt solution, so that is highly concentrated. So our solvent molecules going from that lower concentration to the higher, really diluting it down. And again, that osmotic pressure stopping that continuous flow of those particles. Now, there's also 3 ways that we can describe a solution, and that is isotonic, hypotonic, and hypertonic. And isotonic solutions basically exert the same osmotic pressure as body fluids, and they are typically what IVs are. They're isotonic. And basically, when we think about isotonic solutions, there's kind of 2 sort of values we think of as being isotonic, and that is basically 0.9% mass to volume sodium chloride or a saline solution, some type of salt solution, and 5% mass to volume glucose. These guys are considered basically isotonic. And what that basically will mean is when you put something, for example, like a red blood cell, which is the common example for these type of things, if you drop your red blood cell, which obviously has a membrane and works like a membrane, obviously, into something that is an isotonic solution, the osmotic pressure inside the cell and outside the cell are basically the same. And what that will pretty much allow is pretty much equal flow in and out of the cell, and the cells will be okay. And again, that's why IV solutions are isotonic, because obviously if you're getting an IV, you're probably not in great shape. Maybe are you not in such the best shape, and obviously you don't want to cause any more damage by giving something that's going to screw up your cells, right, and stuff like that. So you want to make sure that the pressure is okay. Now, we have some solutions that are hypotonic, and hypo means less than. So that would be solutions that is less than 0.9% sodium chloride or 5% glucose. And basically, if you take your red blood cell and you drop it into a hypotonic solution, that means outside of the cell is less concentrated than inside the cell. So what's going to happen in that particular situation is osmosis is going to take over, and all the fluid outside of the cell is going to basically rush into the cell because it is more concentrated inside. So again, that effort to sort of dilute down the more concentrated part of it. That's going to basically allow your cells to collect a bunch of fluid, which is probably not so great. That's going to cause it to start to swell and perhaps burst, which is known as hemolysis. And again, not a very good situation. And again, because that is obviously a less concentrated solution on the outside of the cell versus inside the cell. Now, hypertonic solution is the opposite. Hyper is greater than. So that is a solution that's basically greater than 0.9% sodium chloride or 5% glucose. And once again, if you throw your red blood cell into that type of solution, which is hypertonic, that means outside of the cell is actually more concentrated than inside the cell. So what's going to happen is the cell is going to go, okay, outside is more concentrated. I'm going to basically release all of my fluid outside the cell in an effort basically to dilute the outside solution. And that's going to cause some trouble for your cell as it's going to start to shrink and go through what's known as crenation, which is not good as well. So the solutions, and when you put something like a membrane or something like a cell, obviously in there, that acts like a semipermeable membrane, the difference in osmotic pressures can cause the flow of fluids in one direction or the other, and usually not a good result if it's a person that's happening to. Any questions on that there? So here is some pictures. We got some nice healthy cells here. Isotonic solution, nice even sort of flow inside and outside. Looks like a good whole donut there. Here we got the water rushing out of the cell because outside is more concentrated than inside. We get like the donut holes. And here the water is flowing into the cell, swelling it up there, gets your jelly donut that's going to burst, right, in a hypotonic type solution. So let's take a look at a few here. Let's say we had, we put our red blood cell into these different solutions. Let's do 0.1% sodium chloride. Let's do 5% glucose. Let's do 10% glucose. Let's do put it into pure water. All right, so for each of these, will the cell shrink? Will it swell? Will it be okay? Yeah. And what type of solutions you got going on in each of these cases if you put that red blood cell into each of those? Okay, let's take a look. So in this case, isotonic again means 5% glucose and 0.9% mass to volume sodium chloride or any type of sort of salt solution. So when we look at 0.1% sodium chloride, if we were to put it in there, 0.1% obviously is less than 0.9. So that is less than, which means this is a hypotonic solution. And a hypotonic solution means that outside of the cell is less concentrated than inside the cell. So we are going to get this situation right there to happen. The water is going to rush into the cell, going to cause it to swell, right, and burst and go through hemolysis there in that particular case. Any questions on that one there? Now, 5% glucose is a isotonic solution. That means that our cell is going to be okay. We're going to get basically even flow inside and outside of the cell as the osmotic pressure is equal to on both sides, basically, of the cell in this case. So nothing bad will happen in that particular case. Looking at 10% glucose, 10% is definitely higher than 5%. That means that this solution is a hypertonic. Obviously, this solution here was isotonic. And because it's hypotonic, that means outside of the cell is more concentrated than inside the cell. So we're going to get basically all the water and stuff to run out of the cell. And that's going to cause this guy to start to shrink and go through crenation and not be so good. Lastly, here we have pure water. Pure water is a hypotonic solution. So sometimes people think water, right, can't be hurtful, but water has nothing dissolved in it, which means it has no osmotic pressure, which means when you put that cell in there, actually outside of the cell is less concentrated than inside the cell. So once again, you're going to get this stuff to flow inside the cell. It's going to start to swell and burst, which again is hemolysis and not so good. Any questions on those? So it's important to know the cutoffs there. 0.9% sodium chloride and 5% glucose are isotonic. And it is as simple as it's either that number or higher or lower as being hypertonic or hypotonic. Any questions on that there? All right, so dialysis is a process that's similar to osmosis. It allows small solute molecules and ions as well as solvent molecules to pass through. It's a very common process to sort of filter things out, like our kidneys, right? Help do that, filters out stuff in our bodies. And like I said before, kind of earlier, it's also a very common sort of procedure done in sort of research labs, especially if you're dealing with proteins and stuff like that. A lot of times you'll throw things in dialysis bags to sort of incubate those things. And basically, again, it will allow certain guys to pass through and other ones not to get through in terms of these solutions. Any questions on that there? All right, that wraps